All right, so it's my pleasure to introduce the next speaker. It's Ray Perlner from NIST, who's going to present a joint work with Dustin Moody, who is also in the audience. And it's having a title of Vulnerabilities of McEliece in the World of Escher.
Well, Tanya said everything that's on this slide, so on to the next one. So this paper attacks a scheme which is a McEliece variant from 2014, which is called McEliece in the World of Escher by Gligorossi, Samardziska, Jacobson, and Bezatev. It has encryption, it has signatures. The new ideas involve something called error sets, which is the error vectors not characterized anymore by Hamming weight, but by this new concept, list decoding, which is the method used for decryption or the private key operation in general. And so we'll cover the form of the private key, the decoding algorithm, and we'll give information set decoding algorithms for signature forgery and key recovery for both encryption and signatures. And we will briefly discuss whether there are any countermeasures for these. So, like McEliece, we have a generator matrix, or we can characterize either by a generator matrix or a parity check matrix. In one case, you decode the ciphertext. In another case, you decode the hash of the message for signature. And so the trick is finding an error vector with the proper format, satisfying either of these equations. The relation between the public generator matrix and the private generator matrix, or the parity check matrix, is given there, and note that the P in both cases, the permutation is the same. So now we have the non-ordinary McEliece things, the error set concept. And this error set concept is, instead of simply taking a low Hamming weight string like we have here, we are just looking at the 2-bit chunks, or L bits in general, but for the parameters given, it's always 2 bits. And we say, is it 0, 0, 0, 1, or 1, 0? If so, it's a valid error vector. Don't worry about the Hamming weight. But yeah, you can't have 1 1s even if you have very low Hamming weight. So that's the difference. And so all error vectors are equally probable. In this case, all valid. So now we come to the way that these, in their analysis, they characterized the density of the error set. So instead of a Hamming weight, they have this density concept, which is simply basically the entropy per bit. So √3 for 3 possible error vectors in 2 bits, which is the error set used in all the parameters given. Okay, here's what the private key looks like. The generator matrix is up here, and the parity check matrix is down here. We have smaller blocks that are N1 by K1 that correspond to the redundant portion of the generator and parity check matrices. So here's how we decode using this. We break the error vector into chunks, and we try all the possibilities for the first K1 bits, and then we check if that results in any inconsistencies, because this will fix the next n1 bits here, and we use that to prune the list. Then we try the next k2 bits, prune based here on the next n2, and so on, until we've narrowed down to a single possible error vector and can decrypt the message. Now, what's notable here is that in order to do this, we have to set up a list of size exponential in the size k1, in particular row to the k1, so this k1 has to be fairly small for encryption. For signature, it's slightly different. In this case, we don't have to try every possible error vector we can have on the left, but we still do the same thing of generate a list here, check for consistency there, so on and so forth. But the key thing is all the consistency checks in this last block have to be passed by at least one member of our list. So the size of the list needs to be at least 2 over row to the nw, so this dimension of the last block needs to be small in order for decoding to be efficient. So with that in mind, let's carry on to attacks. So the first attack is a direct attack on the error vector. And so the usual framework for information set decoding here is we take the generator matrix, we divide it into a square matrix A and a rectangular matrix B, check that A is invertible, and we will use that to guess the first k bits of the error vector. First we permute the, I mentioned we're permuting it. Yeah, we permute the public generator matrix. We try our permutation. We check that the first square portion is invertible. If we do, we invert it, and that will allow us to guess the first k bits of the error vector. And then we will solve for the rest of the error vector through linear algebra, and then we can check to see if it's of the appropriate format. If it's not, then we try again with a different permutation. So the key point is that we can guess k bits and then just check if the rest, and that will fix the rest of the error vector. So now we'll look at the optimal strategy for guessing, in particular for signatures, where we get the biggest advantage. So the thing to note here is that if you guess a 0 for one of the 2 bits in one of these 2-bit blocks, the other bit is guaranteed to be correct, because 0, 0 and 0, 1 are both okay error vectors. Thus, if we guess only 1 bit in each of these 2-bit blocks, and we can guarantee that based on the choice of permutation, then we can force 2k bits of the error vector to be correct. And n is not that much bigger than 2k for the parameters that were chosen by the scheme. And you can look at what the probability that the rest of the bits are also a correctly formatted error vector, and for the parameters, the probabilities range from 2 to the minus 8 to 2 to the minus 1. Yeah, that's not so good for the scheme. Now, now we can avoid this attack by, so doing this makes the density of the error vector, it makes the Hamming weight like 1/4 of, whereas you'd really expect it to be 1/3 of n. So maybe the legitimate party, the verifier, can enforce that, but that gets you, the probability is √3/2 to the n minus 1.5k, which is still not enough to make the parameters match the claim security level. So you could also increase the ratio n over k, but that will actually worsen some of the other attacks that we'll get to here, the key extraction. So if you look at what information set decoding algorithms do in the most abstract sense, what they're doing is that they find low-weight vectors in the row space of a matrix. So either gpub or hpub has to have low-weight vectors in order for decoding to be efficient, as we showed previously. And gpub and hpub have the same row space as g and h, only related by that permutation, so we can find them just by attacking gpub and hpub. So returning to the private key, let's look. Remind ourselves, this is where the low-weight vectors have to be for signature. This is where the low-weight vectors have to be for encryption. So, okay, so that's fine. We can find those, but what do we do once we have them? Well, so we have these columns, and these are the columns which will be the support of the low-weight vectors that we're targeting. And they'll, of course, be permuted by p, but if we know where these columns land when p acts upon them, then we can figure out what p is, or at least figure out enough about p such that we can reconstruct a private key of the right form. Okay, so here's what happens if you take a real, you look which bits are 1 and how often when you apply an actual information set decoding algorithm to a parity check matrix that looks like that. And you can see, you really can see all the structure. It's, I don't think these were actually the parameters that were in the scheme, but pretty close. So once you have found those columns that you were interested in, you simply remove those columns and start attacking. You'll see what's left over has exactly the same form, except the this red rectangle should be over 1, but has the same form, just one fewer block if you remove the columns and row reduce. So that's how the attack is going to work. So now let's look in a little more detail, because this is going to be useful for some optimizations, how the information set decoding will work. So first we permute the columns of the matrix we're attacking. Check the first part is invertible. And if it is, we can get an identity matrix on the left and some other stuff on the right. And you combine a few rows with so we thereby guarantee low weight on the left, and low weight on the right there. So yeah, so basically what we're doing amounts to guessing, again, k bits or n minus k bits, depending on whether we're attacking the generator or parity matrix of the row after some permutation. And so that when you're guessing low weights, you always almost are going to guess all zeros. So one thing about this scheme, so the verifier has to check that the error vector is divided into these nice 2-bit blocks, so you can't break the 2-bit blocks up. So the permutation is not random. It's only mixing pairs of columns, not columns individually. So, if we're checking blocks where either both columns are in there or both columns are out, it makes sense to keep those columns intact, and so you only can guess. You have to guess one thing instead of guessing two things. So we'll have a non-random permutation. P prime is the same. The second optimization is that you remember that graph had, so the bits we wanted weren't the only ones that were non-zero, but they were the ones that were non-zero the most often. So, what do we do with these sort of spurious columns? And fun trick is we can actually check if we have the right columns or not, because if we get error vectors like on the left, and you remove most of these columns, the rank will fall. Whereas if you remove if you remove the same number of columns and you have vectors like these, the rank usually won't fall. And so you can tell which is which. And once you do that, then you can test all the rest of the columns to see if they're the right sort of columns, because the right sort of column will reduce the rank, and the wrong sort of column will not reduce the rank of the matrix when you remove it. So this gets us to the private key structure much faster than just doing statistics. On average, you need, I think, two vectors from the target set to get this to work. So we implemented this in Sage on a laptop, and it took about a little under 2 hours for the 80-bit parameters for both signature and encryption. So it's less than the claimed 80 bits of security.
Very fast computer.
No, I don't think I don't think NIST can afford that. Sorry. So now we'll look at countermeasures. So one thing you think, well, okay, so they always tried this 2-bit error set. Does it help to change the error set? And it doesn't look like it helps. It looks like it makes the decoding harder faster than it makes the attack easier. So now what you can do is you can increase n over k for encryption, increase n over n minus k for signature, such that you're guessing, you end up guessing having to guess almost all the columns, and so it's very unlikely that if you guess almost all of the columns that they're all zero. So it's in order to make this work for encryption, it makes the key about 300 times bigger, we calculated. But for signature, you don't have to do all that much, except for the fact that when you increase n over n minus k, it makes the signature forgery attack from before worse. And so it doesn't look like there's any trade-off that actually works for signature. At least I couldn't find any. Okay, so the conclusion is this scheme is quite attacked, and maybe you can save the encryption scheme, but it's the attack is quasi-polynomial, and the cost of decryption doesn't seem that great. And this, having a good coding-based signature scheme is really where there's less competition, but the signature scheme, unfortunately, does not appear to be fixable. Thank you. Questions?
Well, thank you for the presentation. It was quite a thorough break. Are there any questions?
It's not completely clear for me. What is the complexity of the second attack?
Of the which attack?
The second one.
What's the I mean, so I guess it's, yeah, I mean, well, it depends what you're varying the parameter. I mean, so it took 2 hours for the parameters given. I think it's, it's polynomial or quasi-polynomial at best in the size of the parameters. So.
Any more questions? We have lots of time. I mean, I'm not going to make you sit here for 15 minutes, but you can really ask more questions. I mean, it's a little hard to ask questions. I'm struggling myself to say, hey, how can you repair it or anything, because it doesn't quite seem fixable. Okay, then, if there's no further questions, then please join me in thanking the speaker again.